a multi-purpose hall having dimension equal to 7 meter by 14.3 meter. Internally, the floor slab of hall supported on 300 mm thick masonry wall. A 300 mm wide RCC beam is placed along the width of the hall, which divides the floor slab into two equal panels, and the live load acting on the slab is 4.0 kN per meter square and floor finishes 1.0 kN per meter square. Now we have to design the floor slab by using M20 grade concrete and Fe415 steel. So here the dimensions of the halls are given. So we have to consider the width of the hall is 14.3 meter internally, and the depth of the hall will be the 7.0 meter. Now we have to arrange the beam having thick 300 mm wide, which is placed exactly midway, so that it will be divide the hall into two panels. One panel having size equal to 7 meter, another panel having size equal to 7 meter. So what we are getting, this is panel number 1. Panel number 1 having thickness equal to 7 meter, and this is panel number 2 having thickness equal to 7 meter, and this is the thickness of your beam, that is width of the beam, that is 300 mm. So this is your RCC beam having size equal to 300 mm, and this is the positions of your wall along the periphery of the halls, and the thickness of the wall will be the 300 mm. The next step is, first step we have to go for the calculation of the aspect ratio, that is Ly by Lx. Ly is nothing but the length of the slab along the longer direction, that is along the y direction, and which is equal to 7 meter, and Lx is nothing but the length of the slab along the shorter span, that is along the x direction, that is Lx, and which is equal to 7 meter. So Ly by Lx, that is 7 divided by 7, we are getting the value equal to 1, and which is less than 2. So here Ly by Lx is less than 2, so given slab is the two-way slab. So we have to design the given slab as a two-way slab. Now we have to go for the calculation of effective depth of the slab. Now effective depth of the slab is given as by the formula D is equal to effective depth of the slab, which is equal to span divided by L by D ratio into modification factor. Now here the span is nothing but we have to consider the span along the shorter direction. It means that we have to consider the span of the slab as a, that is along x direction, and which is equal to 7 meter, and which is equal to 700 millimeter. The next one, L by D ratio. This L by D ratio will be depend upon the support condition. For simply supported, we are considering this as a 20. For continuous, we are considering this is as a 26, and for the cantilever we are considering L by D ratio as a 7. Now here the given slab is a continuous slab, so we have to consider here the slab will be the continuous, so we have to consider this slab as a continuous slab, so we have to adopt L by D ratio as a 26. So we have to put up here L by D as a 26, and this modification factor MF, which is equal to 1.4, and which is again depend upon the type of steel. If you are using Fe250, then the modification factor is 1.65. If you are using Fe250, modification factor is 1.65. If you are using Fe415, the corresponding modification factor is 1.4, and if you are using Fe500, the modification factor is 1.3. So here we are using the Fe415 steel, so we have to use modification factor as a 1.4. So after putting this value, we are getting the effective depth of the slab, which is equal to 192.30. So we have to go for the higher side, so we are getting this effective depth of the slab is equal to 200 millimeter. Now let us assume, or let us provide 10 mm 5 steel bars with clear cover of 15 mm. This is the minimum clear cover we have to provide for the slab, which is equal to 15 mm. Hence overall depth of the slab is given as, this overall depth capital D is equal to effective depth plus clear cover plus half the diameter of the steel bars. So here we are using the 10 mm diameter steel, so 10 divided by 2. So overall depth is equal to 200 plus 15 plus 5. So we are getting this overall depth of the slab is equal to 220 mm. So adopt this as the overall depth of the slab. The next step number 2, we have to go for the calculation of the load. So first live load is directly given 4.0 kilonewton per meter square. Then floor finish is given 1 kilonewton per meter square. The next step, you have to go for the calculation of the self weight of the slab. Now this self weight of the slab is given as B, that is width of the slab, multiply by the depth of the slab, multiply by the unit weight of the concrete. So B is nothing but, we are considering 1 meter wide panel, so it will be B is 1. So D is nothing but overall depth, which is calculated as 220 into unit weight of the concrete is 25. After simplifying this, we are getting the self weight of the slab is equal to 5.5 kilonewton meter square. The next step, you have to go for the calculation of the total load acting on the slab, which is equal to live load plus floor finish plus self weight of the slab. So finally we are getting this total load acting on the slab as a 10.5 kilonewton per meter square. Then third step, that is important step 1, we have to go for the calculation of effective span for the slab, because the bending moment developed in the slab is directly depend upon the effective span that we are using for the slab. Now what IS says that, IS 456 says that formula for calculation of the effective span. So first one, effective span is equal to clear span plus width of the support. Here the clear span is nothing but the dimension of the your hull along the x direction. So clear span, that is 7 meter plus width of the support. So here we are using the 300 mm wide wall. So 7 plus 0.3. So we are getting the effective span as a 7.3 meter. The next also, we have to calculate the effective span along the second consideration. Effective span is equal to clear span plus effective depth of the slab. So 7, that is clear span, plus effective depth of the slab we are calculating as a 200 mm in the step number 1. So it will be 0.2. So we are getting the effective span as a 7.2 meter. So here what IS says that, IS says that we have to use the lesser of these two value, lesser of A at B. So here we are getting the lesser value as 7.20. So in this problem, you have to use the effective span in both direction as a 7.20 meter. So effective span is equal to 7.20 meter. The next step, you have to go for the bending moment calculation. So bending moment along the shorter span is given by the formula mx is equal to alpha x w into lx square. Bending moment along longer span is equal to my is equal to alpha y w into lx square. We have to using the lx in both the cases, along the x direction as well as along the y direction. Alpha x is nothing but the bending moment coefficient. Alpha is again the bending moment coefficient for the longer span, and these values are depends upon the ly by lx ratio. Now here, this is the arrangement of the panel of the slab. So what we are getting, this is only one, this is your panel number 1, this is your panel number 2. So what happened, the given slab is continuous or only one of the side, that is one on the beam. Other 3, suppose if you are considering the panel number 1, this edge of the slab will be the discontinuous one, this edge of the slab is also discontinuous, this edge is also discontinuous, but this edge of the slab will be the continuous. So given type of the slab, so in this problem what we are getting, the given slab is discontinuous over the 3 edges. So this is edge, this is your edge number 1, this is edge number 2, this is your edge number 3. So given slab is discontinuous over the 3 edges and continuous over the one of the edge. So we have to go for this case and calculate the value of the alpha x and alpha y. For that calculation of alpha x and alpha y, you have to refer IS 456 2000, page number 91, table number 26. And in that case, we have to use the case number 7, that is the slab is discontinuous over the 3 edges and continuous over the one of the edge. And we are getting the value of the alpha x and alpha y. Again, for calculating of alpha x and alpha y, you have to first calculate ly by lx ratio with respect to the effective span that we are calculating. So effective span we are considering as 7.2 meter. So this aspect ratio is ly upon lx. The effective span along the y direction will be 7.2. Effective span along the x direction is also 7.2. So what is we are getting, ly by lx is equal to 1. Then bending moment coefficients are given. So here we are getting the two types of the bending moment coefficient. One is for the positive bending moment at continuous edge, positive bending moment at mid span, because the given slab is continuous over the one of the edge. So what is at the continuous edge? We are getting the negative bending moment, and we are getting the positive bending moment at the mid span. So here the alpha x value by referring the IS 456 table number 26, which is available on the page number 91. So we are getting this alpha x for the negative bending moment coefficient. For the Ly by Lx ratio 1, it will be 0.057, and the corresponding alpha y will be the 0, that is not considered because slab will be continuous over one of the edge, that is along the one edge. So positive bending moment at mid span is equal to 0.047. This is the alpha x for the positive bending moment, and this is the alpha y 0.043 that we have to use. Then first we have to calculate the bending moment along the shorter span. So maximum positive bending moment at the continuous support is the maximum negative bending moment at continuous support is given as alpha x w into Lx square. So what is the alpha x value we have to use? Alpha x we have to use as a 0.057. So 0.057. W is nothing but the total load acting on the slab, and the value of the W will be the 10.5. So you have to use this value 10.5 here, and the effective span will be the 7.2. So what we are getting after simplifying this, we are getting the bending moment is 31.02 kilonewton meter, which is equal to 31.02 into 10 to the power 6 Newton millimeter. The next step, we have to calculate the positive bending moment at mid span, which is equal to alpha x w into Lx square. What value of the alpha x we have to use? We have to use the coefficient for the positive bending moment at mid span, that is 0.043. So here we have to use the value as 0.043 into 10.5, that is again total load acting on the slab, 7.2, that is your effective span. So what we are getting? We are getting the positive bending moment as 24.40 kilonewton meter, and which is equal to 23.40 kilonewton into 10 to the power 6 Newton millimeter. The next step, you have to calculate the bending moment along the longer span, and this bending moment along the longer span is given as, we are getting this bending moment is equal to alpha y w into Lx square. So alpha y is 0.043, w is again 10.5 into 7.2. So what is we are getting? Bending moment is equal to 23.04 into 10 to the power 6 Newton millimeter. So here we are getting the bending moment developed along the shorter span as well as the bending moment along the longer span. Then step number 4, we have to go for the check for the depth, whether the whatever may be the depth we are calculating, that is 220 mm, it will be sufficient from the bending moment concentration or not. We have to check that. So bending moment is given by the formula R into BD square. Again, this M, K, J, R, these are called as the constant, design constant. M is nothing but your modular ratio, K is your neutral axis factor, J is your lever arm, and this is your moment of resistance constant, that is your R. So by using these values are depend upon the grade of the material. In the previous problems we have done the calculation regarding to that. So we have to directly adopt. M is 13.33, K that is 0.29, J is 0.9, and R is 0.91. The next one, we have to use the maximum positive bending moment, because here we are getting the two bending moment. This will be 13.02 into 10 to the power 6 kilonewton into 10 to the power 6 Newton millimeter, and this is the another bending moment, that is 23.04, that is into 10 to the power 6 Newton per millimeter. For the checking the depth, we have to use the maximum of that value. So we have to use the 13.02 into 10 to the 13.02 into 10 to the power 6. Then the value of the R is 0.91. The next one, we have to go for the B, that is width. We are considering 1 meter of width of the slab, so it will be the 1000 into D required. We have to calculate from the, after simplifying this one, then we are getting this D required is equal to 184.62 millimeter, when which is less than D provided. What is the depth we are providing? We are providing the depth as a 200 millimeter. So the slab will be the towards the upper side with respect to the bending moment consideration. Once we are getting the bending moments, then we have to go for the calculation of the steel. Now first step, we have to go for the calculation of steel along the shorter span. So along the shorter span, we are getting the two bending moments. First bending moment will be your this one, negative, first one will be your negative bending moment, this one, and second one will be the positive bending moment which will be developed at the mid span of the slab. So to calculate the bending moment along the positive as well as the negative, and we have to calculate the steel depending upon the positive bending moment and the negative bending moment. So first we are getting AST is equal to, formalize, AST is equal to bending moment divided by sigma ST J into D. So this is the value of the bending moment. That is where first we are considering the positive bending moment. So value of the bending moment will be the 23.40 into 10 to the power 6. Then sigma ST, that is permissible stress in steel. We are using the Fe415, so we are getting this value as 230. Then J value, we have to use the J value as a 0.9. Then next one, D is your overall depth, we are adopting as a 200. So after simplifying this one, so we are getting the area of the steel for the positive bending moment will be the 565.21 millimeter square. Then also we have to check for the minimum steel. What IS says that the minimum steel should be the 0.12% of the BD. So 0.12 into 100 into B is your 1000, and the overall depth of the slab will be the 220. So what we are getting, the minimum steel required will be the 224. And what we are providing? We are providing the 565.21. So we have to provide the maximum of this 21, that is maximum of 565 and 264. So we have to provide area of the steel as 565.21 millimeter square. Once we are getting the area of the steel, then we have to go for the calculation of the spacing of the bars. Now let us, what we are providing, we are assuming that 10 mm diameter of the steel bars are to be used. So spacing of the bar is given as S is equal to 1000 AST, small AST divided by capital AST. This small AST is nothing but the area of one bar, and this capital AST is nothing but the total area of the steel we are providing. So 1000, area of one bar is pi by 4 into 10 square into this is the total steel we are providing. So what is this? After simplifying this, we are getting the spacing is equal to 138.88. So we have to go for the lesser one. So what we are adopting? We are adopting spacing as a 130 mm. Then you have to also go for the check for the spacing. The IS says that the spacing should not be greater than. So first one, S is equal to 3 times effective depth, 300 into 600. So also S is equal to 300. So you have to provide the lesser of this 3 value. This is first one 130, second value will be the 600, third value will be the 300. So you have to provide the lesser of this 3 value. Hence what we are adopting? We are adopting the spacing as a 130 mm. Hence we have to go for provide 10 mm diameter steel bars at 130 mm center to center at the mid span, because this is the steel corresponding to your mid span. The next one, steel along the shorter span for the negative bending moment. So AST is again the formula will be the same. Now I have to put up the bending moment as 13.02 into 10 to the power 6. Again the design constant are to be the same. So after simplifying this, we are getting the area of steel is equal to 749.27, and the area of the minimum steel we are already calculating. One area of minimum steel will be the 264. So whatever may be the area of steel we are providing, that is 749.27 millimeter square, which is greater than the millimeter square, which is greater than the AST minimum provided. So you have to provide this one. Now again assume the 10 mm diameter steel bars, then the spacing will be given as, so this S is equal to 1000 area of one bar divided by total AST. So we have to put up here. Then after calculating this value, simplifying this equation, we are getting S is equal to 104.76. So again go to the lesser side. So we are adopting spacing as a 100 mm. So hence we have to provide 10 mm diameter bars at 100 mm center to center. So this is the steel along the shorter span direction. Then we have to go for the calculation of the steel along the longer span. Again the formula will be the same. AST is equal to bending moment divided by sigma ST J into D. So bending moment along the longer span, we are getting the value will be the 23.40 into 10 to the power 6. 230, that is the permissible stress in steel, 0.9, that is the your J value, lever arm constant, and 200 is nothing but your effective depth of the slab. Simplifying this, we are getting 565.24 millimeter square, and which is obviously greater than the minimum steel required one. So again we have to provide 10 mm diameter bars. Then the spacing is given as, so S is equal to 1000 AST divided by capital AST. So S is equal to 1000 pi by 4 8 square into total AST, this one. So S is equal to, we are getting this one 138.87. Again go to the lesser one, so 130 mm. Hence provide 10 mm diameter steel bar at 130 mm center to center. So this is about the calculation of the steel along the shorter span and along the longer span. Now the given slab is the continuous slab. So what we have to do, so this is the continuous edge, and the corners, the slab is directly resting on these walls. So what will happen, the corners are not effectively held down. So you have to go for the calculation of the torsion steel required, because slab is simply supported on the walls. So we have to go for the calculation of the torsion steel. Now area of the IS 456 again define this one. Area of this torsion steel will be the 3/4 of the AST provided in the shorter span. That is positive bending moment you have to consider, and the calculation of the steel from the positive bending moment consideration. So 3/4 of the AST in the shorter span, 56.24. So what is the, we are getting AST is equal to 423.93 mm square. This is the torsion steel. We have to extra steel we have to provide. Then let us provide 8 mm diameter steel bars. Then the spacing is given as S is equal to 1000 pi by 4 8 square divided by AST, that is 423.93. So what is the spacing we are getting after simplifying this? S is equal to 118.51 mm. So what we have to do, we have to use 110 mm as a spacing. Then the length of the torsion steel, again I specify that this length of torsion steel will be provided LX, that is span along shorter span direction, divided by 5. So we have to provide length of torsion steel as up to the 1.44 meter from the face of the wall. Hence the size of the torsion steel mesh will be the 1.44 into 1.4 mm, because the span in the both direction, that is along shorter span it will be 7, along the longer span it will be the 7 meter. So this is about the calculation of the steel. Now next step is go for the check for the shear. Now the shear force is equal to W divided by LX divided by 2. W is again nothing but the total load acting on the slab. 7.2 is again your span divided along the shorter span divided by 2, that is shear force. So we are getting this 37.8 into 10 to the power 3 Newton. Then we have to calculate the shear stress. Tau V is equal to V divided by, that is shear force divided by B into D. Shear force, this is the value of the shear force. B is nothing but the width of the slab we are considering. We are considering the 1 meter, that is 1000 millimeter into overall depth, effective depth of the slab, that is 200. So we are getting the shear stress is equal to, after simplifying this one, we are getting the shear stress is equal to 0.18 Newton per mm square, and which is very less than the shear strength of the concrete. So here the design will be the towards the safer side. Now next one, we have to go for the provision of this steel along the shorter span, along the longer span.